So it's something we're looking into right now. So lensing can also help study density profiles. And of course here we need to somehow get guidance from simulations into what extent X-ray and lensing measurements can be combined to study the density profile. Because the X-ray provides a very good measurement on small scales, whereas the lensing provides a good constraint on large scales. So that's indicated here, where you can see the X-ray in red and lensing in blue. And it's once you combine them, you can do much better. And that's quite important, because if you study density profiles and you use one technique, you end up with correlated errors. So here you see the lensing concentration as a function of X-ray mass, and you can see the same for lensing mass. So you get these very steep relations, and if you're not careful, you think, well, this mass richness, or the mass concentration relation is much steeper than the prediction from numerical simulation, which is rather flat. But once you plot uncorrelated quantities, so the lensing concentration versus X-ray mass or the opposite, suddenly you don't, that disappears. So basically you're plotting uncorrelated quantities, and well, now it doesn't look as nice anymore, but we can really sort of calibrate the mass concentration relation. So just to conclude, lensing studies I think are becoming very important for cluster abundance studies, and in the last few years I've seen a remarkable sort of interest from the cluster community to get lensing masses for their clusters, because it's really realized that just relying on the simulation is not enough. There needs to be a way to connect simulations to the observations. And we're now getting small statistical errors, I think, for the first time, to really calibrate these mass proxies and measure the intrinsic scatter of proxies. But I think it's very important to keep in mind that as the samples increase, the standards have to be raised as well. And so that these analyses become much more sophisticated in terms of like dealing with all kinds of systematics and contaminations. Thank you.
Thank you very much. Okay. Other questions? Yeah.
Could the use of the mass estimation provided by the acoustic technique be useful to constrain density profiles of gas clusters as well, or it is negligible with the to mass and wet lensing mass and X-ray masses estimation?
No, I think that, yeah, so if you look at the various ways to study masses, then dynamical masses are typically rather complicated, but I think with the exception of the caustic method, where you basically look at, well, you take a lot of redshifts and you basically see where the redshift detached, where the galaxies detach from the Hubble flow. I think it hasn't been studied in as much detail as what you would need. So I think also there, again, simulations are very important to see to guide the results. But it's indeed very complementary, so I think there it could work. Yeah, I think the only problem I see is that it's quite limited in sort of the redshift range you could do this. So that this is really more redshift. Like really you would like to do this also all the way out to redshift 1. And I think their caustic methods might not work as well.
Next one is Boo.
That's over there.
So, I mean, I think you have the right philosophy that wherever there's a discrepancy, you're pointing out the problems with X-ray. But I wanted to ask you about a possible lensing issue. Could you put up the next plot of the ratio of masses? Right, so as you go to smaller radii, right, so if you think about projection effects, then as you go to larger radii, the fractional contribution to the lensing mass increases, right? So could that be responsible for part of the trend?
No, because in the ensemble average, the cluster should be spherical. So that is basically accounted for. So when we do this ratio, we include log normal scatter in the fit. So we actually constrain that scatter. And so the next step we want to do is to see how that scatter that we fit compares to just the scatter we'd expect from just the random projections. But keep in mind, the blue points have almost no intrinsic scatter. That's why I can blame. I think I'm safe to blame it on the X-rays because it's out of. So you plot two quantities that don't know about each other, which I think is like the fact that we see no scatter. I think is really amazing.
But I mean, in projection effects, there's the random projection, but there's also structures associated with the cluster that may not be X-ray luminous.
No, but so that would
add to the lensing mass.
yeah, but that would cause a log normal scatter.
So what you see in simulation?
Yeah, well, you just take that scatter is proportional to mass, right? And then you just change it, so it's more or less log normal. Yeah.
All right, next one is Dan.
So on that same issue, on the X-ray side, I would have guessed that the dominant or most likely cause would be uncertainty or lack of knowledge of the distribution of temperature in the core, rather than the channel calibration, which I think is now the steady state.
Well, the last calibration changing by 10%, so it's not clear how stable it is. So that I think, because the XMM, we have also a number of clusters where we have XMM and Chandra, and there you can also make the comparison. You really see it's all driven by Chandra. So I think it's still an open issue what is going on, but it's.
But do you have a temperature distribution for both?
Well, so what do you mean by the temperature distribution?
But,
Yeah. No,
but I mean, the X-ray mass strongly depends on the spatial distribution of temperature. Obviously, the X-ray luminosity depends on the emission measure.
Yeah, so it turns out this is not driven by the temperature; it's driven by the gas mass. So the luminosity.
The gas mass depends on knowledge of the temperature distribution.
Yeah, but if you look at, because you have all these different probes, and you sort of see that well, I didn't show it, but if you make the X-ray mass versus gas mass, these clusters all line up. There's no intrinsic scatter, but if you then, instead of X-ray mass, plot the lensing mass, then suddenly you see a shift. So somehow, for the low entropy systems, the gas masses or the luminosities are all overestimated, but the temperatures seem to be okay. So that, yeah.
Yeah, Ludo.
How weak is recurrency in the clusters you looked at, particularly for the high density cases, 2500?
Oh, so there you still, you start getting sort of in a higher regime, but still the shears are less than 0.1. And don't forget, I'm doing this aperture mass, so most of my signal comes from the larger radii where the signal is small. So this is why I mean, like, this is as hard as cosmic shear. Like, it's not that we look at enormous shears but then, yeah, at a high length. So this is the other reason why an aperture mass is 9, because you really avoid this high shears regime. And also contamination by cluster members is less because of that.